All right, so this is example 2 from 3.2. Okay, and it's analyzing a quadratic function. A frog sitting on a rock, jumps into a pond. The height h in centimeters of the frog above the surface of the water as a function of time in seconds since it jumped can be modeled by the function h of t equals negative 490 t squared plus 150 t plus 25. Where appropriate, answer the following questions to the nearest tenth. Okay, and so this is going to be a quadratic function that will be modeled by a parabola. Okay, and we're going to that's going to be the case for anything basically that's moving through the air and the only force acting on it is gravity. So you'll learn that in physics 30. Okay, so we'll start here by graphing the function. Okay, in graphing the function, we'll use Excel. Okay, I'll do that because I think everybody has access to that. Okay, I know it's going to be a parabola that opens down. Okay, I know that it's going to have, I can tell by the equation that it's going to have a y-intercept at 25. Okay, and I know that, well, I know that it's going to be fairly narrow. Okay. All right, so we're going to show it from a time of 0 where it's actually at a height. Okay, so it's on a ledge. It's going to jump up and then down into the pond. Okay, and this just models height. It doesn't actually model the path of it, just the height and against the time. Okay. Just ignore that part. Okay, so I'm going to graph it using Excel. Okay, so I'm going to have one column of data that's going to have my time in it and my height in the second column. So my time, I'll start with the time of 0, and in height, I'll type the formula. So I start with a plus or an equal sign. Both of them work. And then I know that I'm going to have a factor of negative 490 multiplied by, and where am I going to get my t from? Well, in this case, I'm going to get it from cell A2. So I put A2, and then I make it squared, so to the power of 2. Okay, my middle term is 150 times x, so 150 times A2 again, so it looks over to the left to find that value. And then the constant value of 25. Okay, so I see that at time of 0, I have a height of 25. All right, in the first column for the time, I don't want to have to enter everything, so I'm just going to put that I want the value above, and then I want to add a reasonable value to it, okay? So since we're talking about a frog jumping in the air, I'm thinking that it's not going to be in the air for more than a couple of seconds, probably. And so I probably don't want to go up by very much, okay? So I'm choosing to go up by 0.01, okay? And so when I copy this formula, it actually changes. So in the next cell, it's going to be looking at A3 for the x value. Okay, you go down again, I'll be looking to A4. And since I'm on Excel, I can do a lot of values. Okay, I don't have to worry about doing any calculations, so I can really make as many as I want. Okay, those are all 25 because I haven't entered the t values yet. Okay, so then what I want to do is I just want to copy that formula that's in A3 that always tells it to look above and add 0.01 to get to to get the next t value. Okay, so I have to I just have to copy what's in A3. I guess I wrote it out again and paste it in the remaining cells. Okay. And then I'm just going to have a whole bunch of x values. Okay, and this is going to take me quite a ways, it looks like, right? And once it starts getting to have negative y values, we're not really concerned with that anymore because although the frog could go under the water, it's not going to follow the same pattern probably because then there are other forces acting on the frog. Okay, it will, so it wouldn't follow the same path. Okay. So insert, and then we choose a scatter plot because that plots y as a function of x. And in the scatter plot, you get to choose when you click on that down arrow whether you want dots or dots and lines or just the line. So I just plot the line. Okay. And so that's our parabola, right? Just like we thought, it opens down. And when I said it was narrow, that means that it doesn't look narrow because we've stretched out the x-axis so much compared to the y-axis, okay? But if you had them kind of one-to-one, you'd see a very narrow parabola, okay? So that's graphing the function. B, what is the y-intercept and what does it represent in this situation? Well, the y-intercept is what you get when you set x, or in this case t, equal to 0. Okay, and I mentioned before already that when you do that, both of those first two terms with the t in it will become 0, and you're just left with that third term, okay? So you're just in the form ax squared plus bx plus c. You're basically just left with the c. Okay, so what does that represent in that situation? Well, that's the height of the rock that it's sitting on. So the height of the rock above the surface of the water. Okay, so for B, you might write the rock is 25 centimeters above the water. Okay, the next question is what maximum height does the frog reach? So I'm going to look back. I can see in my values in that column with the h values that it's going up, and then it starts to come down, right? And so you can see that it reaches its peak at about 0.15, okay? And then it starts to come down. Okay, so to the nearest tenth of a second, I know that's going to be 0.2 seconds. Okay, as far as the height, I need the height to the nearest tenth of a meter. Okay, so I'm going to say about 36.5, and I didn't need that 0.15, I just need 0.2. So for C, the frog reaches a maximum height of about 36.5 centimeters at a time of 0.2 seconds, or at about 0.2 seconds. Okay, the frog, when does the frog hit the surface of the water? Well, that's when it's going to come down again to a height of 0. Okay, and again, we're just looking for it to the nearest tenth of a second. So 0.4 is actually an acceptable answer here. Yeah, you can tell by looking at our data here that it's about 0.43, but we don't have to worry about that. Okay, we can just say 0.4 because that's acceptable. Okay, so we can go back and just write that as an answer. Okay, so it hits the water at about 0.4 seconds after it jumps. Okay. E asks us for the domain and the range. Okay, so we know that we're looking at motion of the frog between time values of 0 and about 0.4. Okay, and again, it says to express it in the nearest tenth of a second. So we can say domain is any values of t where okay, I put x by accident, but t is better. So x where 0 is less than or equal to x, which is less than or equal to 0.4, or in other words, x is between 0 and 0.4. And x can be any real number, right? It doesn't have to be an exact second value. It's all the values in between. Okay, there we go. I changed it to a t. Yeah, they all have to be changed. Okay. So anything outside that, it doesn't apply to the situation. Okay, obviously we're not going to have a negative value of t because we're not going to look back into the past before this happened, and we're really only modeling the motion for that 0.4 seconds that it's in the air. Okay, the height has a maximum of 36.5 as we determined in C. Okay, so we know that h is greater than or equal to 0 and it's less than or equal to 36.5. Okay, and that's also an element of the set of real numbers. Okay. And yeah, so that's the domain and the range. And then the last question is how far or how high is the frog at a time of 0.25 seconds. So we can just easily look back to our data table that Excel generated for us. Okay, and so if you look at that data point there where t is equal to 0.25, the height is 31.9. Okay, so pretty easy to do, especially if you do it on Excel. It's a little different if you use a graphing calculator. Okay, and so if you did manage to get a hold of one of those from your school, if your school has any extra ones, you might want to ask somebody to show you how to do that. I don't actually have a simulator for the computer for that, but it's fairly easy to do. Okay, so the height after 0.25 seconds is 31.9 centimeters. Okay, so that's the whole question right there.